So welcome to another Mathologer video. A squared plus b squared equals c squared. Forget about Euler's formula and company. Pythagoras' theorem beats them all in just about every conceivable way, at least in my books. Okay, so finally a Mathologer video about the theorem of theorems. My main mission today is to chase down the all-time greatest, simplest, no-brainer proof of Pythagoras' theorem, just for you. At the same time, I'll introduce you to some truly gorgeous, crazy and divine Pythagorean facts off the beaten track. And to finish off the video, I'll tell you a little bit about a new book by me and Marty that has just appeared. Before we get started with the maths, let's do a little debunking. Pythagoras' theorem is a misnomer. The basic fact about right-angled triangles named after Pythagoras was not discovered by Pythagoras at all, and was actually known to the ancient Babylonians at least 1,000 years before Pythagoras was born. Also, although it's often claimed that Pythagoras was the first to have produced a rigorous proof of this theorem, there actually does not seem to exist any evidence to support this claim, and plenty of maths historians doubt it. Now, Pythagoras was the leader of a very influential mathematical cult, the Pythagoreans, who were in the habit of attributing all results originating with them to Pythagoras himself. And it's likely that because of this practice, Pythagoras' name came to be attached to the theorem. Anyway, it's too late now, it's all gone. And so I'll also call the theorem Pythagoras' theorem, or simply Pythagoras. Okay, let's get started by looking at a couple of gorgeous proofs of Pythagoras' theorem. Here's my take on one of the simplest, most beautiful and most popular. Let's make 4 copies of a right-angled triangle with short sides AB and hypotenuse C. Now we arrange these 4 triangles in a square, which at the same time creates a smaller tilted square inside. So the small square is what you get when you partially cover this big blue square by the triangles. The small square has sides of length what? Well, the length is just the length of the hypotenuse of our triangle, which is c, and so the area of the small square is equal to c squared. Let's shift one of the triangles. Now, how large is the modified blue area that you see here? Well, the triangle covers just as much blue as before, and so the new blue area is just as large as before, c squared. Let's do some more shifting. How large is the new blue area? Well, obviously still c squared, right? Now comes the punchline. Shift again. Obviously the blue area is still c squared. However, it's also a squared plus b squared. And so a squared plus b squared equals c squared. Super neat, isn't it? Now, it all seems pretty convincing, but it's definitely important to stress that for this argument to count as a bulletproof proof, we'd have to check some more details. For example, in this diagram here, we need to check that the 2 square-looking shapes are really squares, no matter what right triangle we start with. Not hard, but not a step we can afford to skip. After all, looks can be deceiving. That's as true in maths as it is in life. Just to give you an idea what a more complete proof looks like, let me show you a proof of Pythagoras' theorem in the most famous maths textbook ever written, the 2,000-plus-year-old Elements by the ancient Greek mathematician Euclid. Here's a translation. Whoa, what happened here? It just looked very neat, didn't it? But no, now it's really pretty off-putting, isn't it? And actually also pretty hard to understand just based on this diagram and the text. On the other hand, we can also capture the gist of this classic proof, 2,000 years and still going strong, with a pretty animation. Now, if Euclid had an animation, it's been lost. So here's mine. So Euclid proves Pythagoras by showing that the 2 orange figures have the same area, and the same for the 2 blue figures. Then we've got orange plus blue on top, which is a squared plus b squared, is equal to orange plus blue at the bottom, which is c squared. Here's my take on Euclid's argument. The little orange square is what you get when you cover this larger orange region by this white copy of our right-angled triangle. Then, shifting the triangle as before does not change the area, right? The same can be done with the blue square. Let's do it. Now the orange parallelogram is just this larger orange figure here after being covered by the little red triangle. And shifting the triangle, the area stays unchanged again. And the same with the blue parallelogram. And with pretty much the same diagram as before materializing, we are done. There's the c squared again, and it is now also clear that the orange and blue squares we started with are equal in size to these orange and blue rectangles. Over the millennia, hundreds of different proofs of Pythagoras' theorem have been found, and there's even a book that lists 371 of them. And that's definitely 371 more than most people know. There's the book. I've got about 20 of the most beautiful proofs memorized.
Really?
Really. 20 at least. Let me now show you another of my favorites. Here's our ABC triangle again. Let's scale it up by a factor c. The new triangle has sides AC, BC and CC. We now scale another copy of the original triangle by b. Okay, let's do it. Right. And one more copy of the triangle, we scale that one by a. There we go. Now let's have a close look. And so what we see is that these two sides are the same, and so are these other two. And this means that the three triangles fit together into a rectangle like this. And so a squared plus b squared equals c squared. Absolutely gorgeous, isn't it? And there are lots and lots of other proofs that are just as beautiful as the ones I've shown you. For example, you should check out the proofs discovered by Leonardo da Vinci and the one discovered by American President Garfield. If you're keen to find out more, there's no need to dig up the book I mentioned earlier. Instead, have a look at the nicely illustrated list of about 120 proofs on the absolutely amazing Cut the Knot website. So there, I'm just scrolling really quick. Oh, and just in case the current American President Donald Trump ever tweets his own proof, please someone let me know immediately, all right? Okay. All those proofs that I've shown you so far are great, but none of them is the simplest. I know that this will sound very strange, but the simplest proof for Pythagoras' theorem is a proof of a very, very general super theorem that features Pythagoras' theorem as just one of infinitely many special cases. So what I'm saying is that proving the general theorem, which comprises infinitely many special cases, is easier than proving Pythagoras' theorem, which is just one of these special cases. Super weird, huh? Well, we'll see. Now, what's this super theorem? Well, Pythagoras says that if we attach three suitably scaled copies of a square in the same way to the sides of a right-angled triangle, then the two smaller squares together equal the larger square. It turns out, and that's the super theorem, that the same is true if we replace the squares by any other shape. For example, the areas of the little semicircles add exactly to the area of the large one. The areas of the little pentagons add exactly to the area of the large one, and so on. Okay. That's Pythagoras. That this super theorem is true actually follows from Pythagoras' theorem. To see this, let's just focus on the semicircles and the squares. It's clear that every one of the semicircles occupies the same fraction of the corresponding square. In fact, a quick pi calculation, and it's an exercise for you, shows that every one of the semicircles has about 39% of the area of the corresponding square. But since the two smaller squares add to the larger square, 0.39 times the smaller squares adds to 0.39 times the larger square. Like that. And that's the same as saying that the two smaller semicircles add to the large semicircle. So Pythagoras for squares implies Pythagoras for semicircles. But using exactly the same argument, it also follows that Pythagoras for squares implies Pythagoras for all other shapes. In fact, even stronger. And again, using exactly the same argument, Pythagoras for any shape whatsoever implies Pythagoras for all other shapes. Now, just to make sure that there's no misunderstanding what I mean by this, let me rephrase what I just said. If we can prove from scratch that Pythagoras is true for some special shape, then this proof implies immediately that Pythagoras is true for all other shapes. How amazing is that? But this insight then prompts a natural question. Is there one best, super terrific, perfect shape for which it's easiest to see that Pythagoras is true? It turns out there is. Have a look at this. Wait for it. Done! That's the easiest proof of Pythagoras. Now, just in case you think I've gone crazy, note that you're actually looking at 3 triangles and not just 2. Okay? And that the 2 smaller ones obviously add to the larger one. Like that. And that the 3 triangles are similar because they have the same angles. And that they attach a la Pythagoras to the original red triangle, like this. Really done. There, the simplest proof of Pythagoras using the simplest imaginable shape, the right-angled triangle itself. Pretty bloody amazing, as we say down under. Definitely something for real maths connoisseurs to savor. Okay, before we get into Pythagorean superfacts, here's a little puzzle for you. You go to a pizza shop and as usual they have small, medium and large pizzas. It turns out that 1 small plus 1 medium together cost exactly the same as 1 large pizza. Now, using only a pizza knife, decide which is the better deal, the small plus medium combo or the large pizza by itself. Leave your answers in the comments, and while you're at it, also let me know which of the proofs of Pythagoras you like best. Now, Pythagoras is great, but it only works for right-angled triangles. What about other triangles? Well, there's also a really nice generalization of Pythagoras hidden in school mathematics that applies to all triangles. For this, let's have another look at Euclid's proof. It turns out that the equality of areas of the same color in this diagram generalizes to other triangles, like this. So in this diagram, any 2 rectangles of the same color are equal. Now, with a little trigonometry, the proof is quite simple. Let me just show you how you can see that the 2 green rectangles really have the same area. So we just label the sides ABC and the angle opposite C gamma. Then you can read straight off this diagram here that the 2 green rectangles both have area A times B times cos gamma. And that's yet another exercise for you. You'll be very busy today. And so the green rectangles have equal area. And with that insight, we get the sum of the top 2 squares, a squared plus b squared, minus the 2 green bits, so minus 2 times ab cos gamma, equals c squared. Of course, most of you will encounter this Pythagoras under the name cosine rule. So in the case that the angle is 90 degrees, cos is 0, and the cosine rule turns into standard Pythagoras. When it comes to the cosine rule, the next best triangle angles beside 90 degrees are 60 and 120 degrees. Why? Because cos 60 is 1/2 and cos 120 is minus 1/2. For example, for 60 degrees, the cosine rule takes on this particularly nice form. And for 120 degrees, we get a plus sign there. Almost as pretty as the 90-degree Pythagoras. And who knows, maybe in a world of giant bees, in which the hexagon's 120-degree angles dominate, this is the Pythagoras. Anyway, here's another little puzzle for you. One remarkable thing about Pythagoras is the existence of Pythagorean triples. These are triples of positive integer ABC, such that a squared plus b squared equals c squared. Like, for example, 3 squared plus 4 squared equals 5 squared. How about the 60 and 120 degree Pythagoras? Can you find non-trivial positive integer triples ABC that satisfy these other 2 Pythagorean equations? People always think that since Pythagoras has been around for thousands of years, they know everything worth knowing, and there's nothing new to be discovered about it. Wrong. New proofs and fascinating Pythagoreanish facts are still being discovered, and there's so much beautiful stuff that hardly anybody has heard of. For example, Marty and I just recently discovered a proof of Pythagoras' theorem that seems to be new.
Oh, what? Really?
Yeah, actually it was new to me too, but actually if you look at the cut the knot side, in the list there is a proof by us, and I had a look. Yeah, actually what we did there amounts to a new proof. Anyway, it's there. Anyway, so to finish off, here's just a little gallery of really interesting Pythagorean flavored theorems that will culminate in my all-time favorite in this respect, the Gwass Theorem. So a squared plus b squared equals c squared, but if this height here is d, then 1 over a squared plus 1 over b squared equals 1 over d squared. Hands up, who knew that?
My hand was down.
Well, it's really easy to prove. Give it a try. Now, theorem 2. This one works for arbitrary triangles. Drawing these connections here, x, y, z, then x squared plus y squared plus z squared is equal to a squared plus b squared plus c squared times 3. And every single one of these new green triangles here has the same area as the red one we started with. Not easy to prove, but feel free to give it a try anyway. Theorem 3. Suppose we had started with an ABC right-angled triangle, and then throw squares on the sides of the green triangles like this. Then the yellow square is equal to c squared, and 5 times the yellow squared is equal to the sum of the 2 orange squares. Pretty amazing. Why 5? Why anything nice? And we can keep on going. Adding the pink squares here, the sum of the 2 small pink squares is equal to the large pink square. How unexpected and how pretty is that? And there seems to be many similar relationships to be discovered if we keep extending this way. Okay, now to really finish off, let me tell you about higher dimensional counterparts of Pythagoras' theorem. The first counterpart many of you will be familiar with. To begin, let's restate Pythagoras in terms of rectangles. In a rectangle with sides a and b and diagonal c, we've got, well, a squared plus b squared equals c squared. This version of Pythagoras has one straightforward counterpart in 3D, where we replace the rectangle with a rectangular box, like this. Now, if its sides are a, b, c and its diagonal is d, then a squared plus b squared plus c squared equals d squared. And this works in all dimensions. So for a 4D box with sides a, b, c, d and diagonal e, we've got a squared plus b squared plus c squared plus d squared equals e squared. Okay, most of you would know this, but did you know that there is a second, totally different and totally crazy way in which Pythagoras generalizes to all higher dimensions? It is called the Gwass Theorem, and the 3D version was only discovered in the 18th century by the mathematician Jean-Paul de Guar Theorem. To motivate it, we interpret this right-angled triangle as what we get when we cut a corner of a rectangle, like that. In 3D, cutting off the corner of our box, we get this. That's a triangular pyramid with the red cut forming the base of this pyramid, and we've also got 3 faces that are all right-angled triangles. Now, if A, B and C are the areas, so no longer distances, so the areas of the right-angled triangles, and D is the area of the red base, then the Gwass theorem says that a squared plus b squared plus c squared equals d squared. I absolutely love this one. I find it so surprising that this should work for squared areas instead of squared distances. And not only in 3D, but also in all higher dimensions, where what's squared are volumes and hypervolumes. I often assign the easy proof of the 3D fact in assignments at uni. So maybe you'd like to try your hand at this one too. As I said, lots and lots and lots of homework for you today. Again, these are just some examples of tons of stunning Pythagorean facts. If you enjoyed this video, make sure to also check out some of the links in the description, and in particular the cut the knot list of proofs, which also contains Marty and my new proof of Pythagoras. And that's it for today. Except I also wanted to tell you about a new book by me and Marty, which has just been published by the American Mathematical Society. For about 8 years, Marty and I wrote a weekly maths column for one of the big newspapers here in Australia. And this book is a collection of 64 of these articles, all with an Australian theme. The book has come out really, really nice. It's in full color, it looks great. And so if you like the videos, here's an opportunity to bridge the time between videos and to find out about the prehistory of the Mathologer. In general, have a look at qedcat.com. That's Marty's and my website for all things mathematical, especially our mathematical movie database, our mathematical movie clip collection, our other books, articles, etc. And that's really, finally, it for today.